Okay, so continuing this problem, I can ask also if going from launch to landing, I can ask, well, what's the final velocity right before it hits the ground? And if it is a perfect horizontal flat surface and lands the same height that it was released, you don't actually have to do any calculations to find the velocity right before it lands, because it's kind of symmetric. If we are launched 6.9 degrees at 10 meters a second overall, we have the components of 8 meters a second in the x direction and 6 meters per second in the y direction. When it lands, it has the same values of those speeds in terms of the components, except the direction for the y component is flipped. Again, the x motion remains consistent throughout the entire trip. So obviously, we know that the x direction is going to be 8.0 meters a second. The y velocity, again, only if it lands at the same height at which it was launched, it's going to have a value of 6 meters a second, except it's going to be pointing downward. And yes, I know I have the vector here because at this point, right before it hits the ground, we're going to have x motion this way and y motion this way. But again, if I want to find this resulting velocity, I need to rearrange those vectors head to tail. So I'm going to take that same vector, I'm going to put it here. And then, you can add it together and find that V2 overall. But again, I don't need to do a calculation in this particular example. I know that V2 is going to also be worth 10 meters a second. But this time the angle is going to be the 36.9 degrees below the horizontal. Now, if I want a velocity anywhere else along the pathway, then this shortcut isn't going to work. I'm going to have to do the work and the calculations. I'm going to have to find quite a number of things. But we'll get into that a little later. Before I get into that, I do want to talk about finding max height. What is that max height? What is the delta y max? And the question is, well, okay, where does that occur? No, I'm going to leave that. Where does that occur? Where does the maximum height occur? Well, top of the arc. And I've made a notation that's at point C. So here's the thing. In the previous example, we did all this work from point A to B. Great, awesome. But when you analyze another point along the trip, you have to start completely over with your work. You can't use the information, or a good portion of the information, from when I went from A to B. Because it's a different part of the problem. It's going different distances, different times. It's all different. The only thing that is consistent is the beginning information. Yes, it was the same launch speed, same angle. So I can keep my initial x and y velocities, but I do have to make a notation that I'm going to go from A to point C here, from here to here. And that creates other differences in my information. Now, there's some things from last problem we can kind of keep, but you don't have to. Or maybe you were just given find max height and you didn't do the range and the hang time. So we can, in the x direction, we know in the x direction it goes from here to here. So really in the x direction it's going to go from here to here. In this particular part of the problem, we're not doing the full range. In this part of the problem, from A to C, we're only going from here to here. Now, some of you are savvy and say, well, isn't that half the distance from the previous part of the problem? So don't we kind of know that? And the answer is yes. And some of you are savvy and say, well, if we know that's half the distance, isn't that going to be half the time that we found the last part of the problem? And the answer again is yes, absolutely. So we could, if we had done other parts of the problem from other point to point, some of that information may translate if you just manipulate it. Sometimes it won't, because sometimes we're not going to have a nice symmetric problem. So you have to be careful, and you're going to have to find information. So we kind of know these, and I'll put them up reluctantly. It was, I think, the time was 1.22 divided by 2, right? Because that would be half the time. And I erased the other thing, so 9.76. So that would be 9.76 divided by 2. So we do know that, but other times and other problems you might not know that. The delta y is what we're looking for here. We're looking for a maximum height, and I don't know what that is. It's at a height. I do know the initial speed in the y direction was 6 meters a second. I know that was shot upward. And I also know that at maximum height, because remember, this is as if it were just thrown straight upward. At maximum height, I do know that instantaneous velocity for a moment is 0. Because that's when we stop moving up and we start moving down. You're turning around. I do know that. And I know acceleration is negative 9.81. And again, this all assumes, all of these problems assume air resistance is negligible. And I also happen to kind of know the time from what last part of the problem. Although, these bits of information that I found from last part of the problem, I'm not going to use to answer this max height question. Because what if I did those wrong? What if I messed that up? You know, if you can use less manipulated data to find your answers, then use the less manipulated data. Try to use as much original data as you can. Well, I mean, yes, I did manipulate the components here to find those, but they're less manipulated than using those components to find all this information from previous parts. So I'm going to stick with only the given information or the conceptual information to find out this maximum height. And I'm going to do this from the y direction. Because the x direction is done. I don't need to do anything else to that. So the y direction is I'm looking for delta y. Okay. Well, if I use the if I use the time independent equation, from acceleration from the y direction, and I happen to know that this is 0, and I happen to know this is positive 6 squared. I can go and manipulate this and find delta y. And I'll do that. So I will .83. So 1.83 meters of height it's going to go. Okay. So I know a good amount of information. All that I knew in the beginning of the problem was the launch speed. And I was able to find out everything else. I'm going to do one more part to really mess with this. And then I'll get you cracking on a bunch of problems. So let me clean this up, and I'll be right back.